For problem 20, I found it best to split up this image of a complex capacitor into 3 individual capacitors. To redraw this image, I shifted dielectric down to the bottom plate. Reasoning behind this is so I can set up the bottom half of this parallel plate capacitor in parallel, and then the top and the bottom half can be added together in series. The reason the bottom half is going to be in parallel is they have the same potential. That's the reasoning behind setting them to have the same distance and touching the same middle portion of this capacitor and having the same bottom plate. For the first capacitor extracted from the previous image, we can see by the equation epsilon naught times the area over the distance that we can just plug in the dimensions and yield a result of 3.3 times 10 to the negative 9 farads. For capacitor 2, we only want the outer portion. We'll consider the dielectric as capacitor 3. So for capacitor 2, we use the same equation, and the difference when we plug things in is we take the outer radius and subtract the inner radius, which is the dielectric, because we don't want to consider that for this second capacitor, which yields the result of 2.5 times 10 to the negative 9 farads. And then for the third capacitor, this is just a dielectric. We can just consider the radius of the dielectric itself for the equation, but we do have to multiply by the dielectric constant, which is 2, and that's what yields a result of 1.7 times 10 to the negative 9 farads. And we can go ahead and add the capacitors 2 and 3 together in parallel, as they do have the same potential across them, and that would be added with capacitor 1 in series, because they do not have the same potential across from them, even though they are following each other. So the setting up the formula, plugging in the values we got for capacitors 1, 2, and 3, will yield us the answer of choice B, 1.8 times 10 to the negative 9 farads.